Again, congratulations on braving the cold. I guess we're going to have a few more of these days before this winter decides to let up. I don't think I have any announcements this morning. You guys have any questions before we jump in? Just keep on the horizon. You do have a homework assignment due next Friday, so keep that in mind. Okay. Well, we're going to resume our discussion with of Chapter 3 today, specifically Section 3.3. Again, we're talking here about expected values. And a little bit of review from what we talked about on Wednesday. We'll jump back in top of page 7 of your Chapter 3 notes here in a sec. So in Section 3.2, we talked about probability distributions. We talked about the probability mass function, which was where we were able to calculate the probability of each value, x equals 1, 2, 3, or so on. And also talked about the cumulative distribution function, the CDF, which is sort of an equivalent way of specifying the distribution. The cumulative distribution function, you're sort of looking at cumulative probabilities, so adding up each of those values for the PMF. And then kind of an important thing that we can use that the PMF for is to find the expected value, or find some numerical summaries of that random variable, things like the expected value, and we'll see later today the variance. So again, this expected value kind of gives a typical value of x of the random variable if you were to do the experiment many times in a row. And so how do we calculate this thing? Again, we saw that to find the expected value, we're going to call it mu, and maybe put a subscript of an x on there. You just add up all the possible values of that random variable. So all possible values. And then you're going to weight those values weighted by probability. So you're going to take all the possible values of that random variable, you're going to weight that by what the probability of getting that outcome is, and add them all up, and that's going to be our expected value. And again, this kind of gives us a measure of center. As we'll see later, you can kind of think of this as a balancing point for the distribution. Different interpretations like that. So then we looked at a few properties, but before I go on, I actually wanted to jump ahead in the notes a little bit. This is an example we'll see on the next page. We'll just kind of motivate you and kind of remind you or show you what we're doing here. So we'll come back to this example in a minute, but if I let my random variable x be the number of dots facing up after I roll a dice. So I roll a dice and I see what's facing up. How many dots would you expect to face up? So if you roll the dice, sort of what's your expected value, or what's the expected number that you might get? And so we can calculate that using our formula. So this example is actually starting on page 8, and I just wanted to kind of quickly show this to you, and we'll come back to it. So yeah, and I guess I should say I'm rolling a 6-sided die here. So x could be 1, 2, 3, 4, 5, or 6, and we're assuming the probabilities are. We're assuming the equal probabilities, right? So the probability of rolling any number is just 1 out of 6. So here we go. We can find the expected value of x, and this is just, again, we're going to take all the possible values of x and multiply by their probabilities and add all that up. So again, this is the sum of x equals 1 up to 6 of x times 1/6. So we're saying the probability of each of those getting any roll is 1/6. So this is just 1 times 1 over 6. We can also get a 2 with 1/6 probability, a 3 with 1/6 probability, and so on. All the way up to 6. So there I'm listing out each outcome. So I can roll a 1 with a 1/6 probability. I can roll a 2 with a 1/6 probability, and so on. And if I add all those up, so this actually ends up just being 1 plus 2 plus 3 all over 6, which is 3.5. This is kind of a trivial example, I guess, but just to kind of motivate how we're doing this calculation, and this is able to tell us kind of what, if I were to roll the dice, what would how many dots would I expect to get if I did this over and over? And of course, you can't roll 3.5 dots. This is just kind of a way to, and so maybe more in this case, it's more of a way to think about where the center of this distribution is going to be lying. But anyway, so we'll come back to this example in just a sec. But I just wanted to kind of do a quick calculation of this, show you what we're talking about. Okay, so we looked at then. Now we're at the top of page 7 of your notes again. So we could generalize that last formula that we saw. So instead of just the expected value of x, we can look at the expected value of a function of x, and the calculation just changes slightly. But still the same idea. And so a few properties here of this expected value, and these are nice tricks that you can use that will speed up your calculations. So if A and B are fixed constants, so there's some number A and some number B, the expected value of a constant is just that constant. We also have this nice linear property with the expectation, so the expected value of A times x plus B is just A times the expected value of x plus B. And that's number 2 is actually sort of the general case of 3 and 4. That if you have some linear function of x, it's very, very easy to quickly calculate that using just the expected value of x. So these are tools that we'll want to use a lot, and we'll show in this next example I'll actually use some of these. Okay, well let's do a slightly more advanced example here to kind of show you how to use these things. So now we're talking about a computer store that has purchased 3 computers. So pick your favorite kind of computer and pretend it costs $500. And so the store is again going to sell them for $1,000. And if they happen to not sell some of these computers, the manufacturer will buy them back after a certain time for $200. So the store buys computers, they're going to try to sell them, and then they can sell them back if they don't happen to sell them. So we're going to let X denote the number of computers sold out of these 3 computers. So we're keeping it small. And we're going to suppose that the probabilities for each one of those outcomes is listed there. So the probability that they sell 0 of those 3 computers is 0.1, and so on up there to selling all of them as a 0.4 probability. Okay, so we're just given the PMF, and we can now use this to answer a few questions. So what is the expected number of computers sold? So how many computers should this store expect to sell given those probabilities? So again, using our formula, the expected value, the expected number of computers sold, that's the expected value of X. And that's the sum of X equals 0 up to 3 of X times the probability of X. So I actually read out what this is. So we could sell 0 computers with a 0.1 probability. We could sell 1 computer with a 20% probability, 2 computers with a 30% probability, and 3 with a 0.4 probability. And if you calculate that out, that should give you 2. So the store should expect to sell 2 of these 3 computers, I guess, based on that probability mass function that we just saw before. Okay, that's pretty straightforward. A little more advanced here. What is so if that's the expected number of computers we sell, what's the expected profit that this store makes? This is maybe more interesting to the store. Okay, so the profit, we can think about the profit's going to be some function of how many computers I've sold, right? So if we let's let y equal the profit of the store. Let's think about what that profit is going to be. So first of all, they've purchased these 3 computers for $500 a piece. So they're in the hole $1,500 to start out with. They spend $1,500 on those 3 computers. But then they make $1,000 per computer that they sell. So if they sell X computers, they're going to make $1,000 times that many computers. And then if they happen to not sell any of those computers, they can sell them back. So they'll get $200 for each computer that they don't sell. So we could write that down as 3 minus X. So however many of those 3 computers they don't sell, they get $200 back. So again, the profit, they spend $1,500 on the computers, they get $1,000 back per computer they sell, and they can resell those things. So we can simplify this a little bit. This is 800x minus 900. Everybody with me? Are we okay? And where we get all this formula? So once we have that, now it's pretty straightforward to find out what the expected profit is. So again, the expected profit is the expected value of y, which, as we just saw, is equal to the expected value of 800 x minus 900. And now I can use some tricks here that we saw on the previous or 2 previous slides. We know this is like expected value of ax plus b. So this is 800 times the expected value of x minus 900. Again, the expected value of x was 2, so 800 times 2 minus 900 is $700. So the store could expect to make about $700 on these 3 computers. So this is this sort of the tools that we saw before, maybe to kind of highlight that they're useful because we can find the expected value of y without having to calculate the PMF of y. So using the proposition and the special cases, we can find the expected value of y without having to derive the PMF of y. So there's only 3 computers, right? You could calculate for each one of those. For each number that they sell, you could calculate the profit and find the probability of each of those things happening. Or we can kind of simplify our lives here and just use the information we already know and figure out how to formulate this in terms of x, and then use our special cases there. Questions, comments on this example? Are we all on board? Yeah.
Because y is already in terms of x there, do we even need to use the special cases?
So because y is already in terms of x, do you need to use the special cases? No, I guess you wouldn't have to. So that would be down here. You could derive the PMF of y and then calculate it anyway. Is that what you mean?
Well, yeah, if you just look at it, it's negative 1500 plus 100x. We already know that you can expect two computers.
Yeah. So you've already known that we've expected two computers to be sold, so you could just jump ahead and calculate it that way if you want. Just kind of stepping through it very, very formally here. Okay. So that's a brief introduction to expected values. And like I said, you can kind of, the way to think about this what the expected value is, other than sort of a typical value, is that it's the balancing point of the distribution. So here I've given you two pictures of PMFs. So for two different random variables. Here's their PMF, and yeah, you can see that the expected value is kind of right in the middle of that. If you could imagine the distribution there as being kind of like a solid shape, it would balance right on where the expected value is. So that's another way to think about the expected value. But I also wanted to show you this picture, excuse me, because this kind of highlights sort of a secondary thing that we need to talk about. So if you were trying to describe both of these distributions, kind of whatever the random variable is, if you're trying to say something about its distribution, they have the same expected value. So their mean is the expected value for each of these things is 4. But they're very different, right? They look very different. So we want to be able to have something else to talk about how these distributions look. And this brings us to this idea of variance. So let's talk about what this is. So for a particular random variable with a PMF, we can find its expected value mu. The variance is going to be this formula here. And kind of the main idea that it provides a measure of how spread out, or how variable that random variable is. How spread out or how scrunched up is it. And so our formula is here. We're just taking it's sort of a glorified expected value there. The variance, which we're going to use remind us of our Greek letters. We have a sigma there. Sigma squared is going to be our symbol for the variance. And it's just the expected value of x minus mu, and we're going to square that thing. And so that's what the variance is. Another thing that you might more commonly hear is the standard deviation. Has anybody heard that word before? Yeah, that's maybe a little familiar. So the standard deviation is actually just the square root of the variance. So whatever the variance is, just take the square root to get the standard deviation. And the reason we sort of make this distinction is that the variance, if you think about the units that it's in up there, it's in some sort of squared units, which doesn't always make sense, whereas the standard deviation is back in the original units of that random variable. So we'll see in a second why talking about the variance interpretation is a little strange. So that's why we want to use the standard deviation. So anyway, again, the expected value, the mean, is just the way of talking about where a distribution is centered, kind of what a typical value is. And the variance we're going to use to talk about sort of how spread out or how squished in the distribution looks if you were to make a graph of something like that of the distribution. So a quick proposition, a quick shortcut that we can use to calculate the variance is by this formula here. So this thing by definition equals the expected value of x minus mu squared. And instead of, so you can calculate it that way, or an equivalent way of calculating is to just take the expected value of x squared and then subtract off its mean squared. So if you want to find those two things can often be easier to find than doing the whole calculation. So I'm not going to derive why that is true. It's not that difficult if you guys want to give it a try to see if you can prove why that's the case. But it's a shortcut of how to calculate the expected value, the variance of a random variable. Okay, so let's get back to our rolling the dice example. So we already calculated the expected value of this thing. Just write this out formally. The probability that x, the PMF, is just 1/6 for x equals 1 to. So that's the PMF. The probability of getting any of those particular rolls is just 1/6. And we already found that the expected value of x is 3.5. So now we want to calculate so we found the expected value and we want to calculate the variance of x. Okay, so again, the variance, well, let me write it down. So the variance of x, we're using sigma squared, is equal to the expected value of x minus its mean squared. So the mean of x here is 3.5, so x minus 3.5 squared. And again, kind of calculating it sort of straight out here. Again, this is going to be equal to 1/6 times 1 minus 3.5 squared. So I can also get a 2. And I could do that for each one of my outcomes all the way up to 6 minus 3.5 squared. So I'm just not writing down what all those things are. So again, just taking the probability of each x times x minus the mean squared. Or I can just use the formula here that this is equal to the expected value of x squared minus the expected value of x whole quantity squared. So what is the expected value of x squared? Well, this is calculated just like that. Going back to that function of x, we can take 1 squared times 1/6 plus 2 squared times 1/6. So just each value of x squared and multiply that by its probability. All the way up to 6 squared times 1/6. And that's actually going to be 91 divided by 6. So the expected value of the square of whatever you're going to see when you roll the dice is 91/6. Which it's important to note is not the same as the expected value of x quantity squared, right? So that's different than taking 3.5 squared. So slight, just make sure to keep that straight. So anyway, our variance then is 91/6 minus 3.5 squared, which is 35/12. Just less than 3. And then you can also write down that the standard deviation is, let's use our sigma, is the square root of 35/12. So is this all making sense? You guys with me on how we're actually, at least how we're doing the calculations? Okay. Well, so just like we had some sort of general properties, shortcuts for expectation, there's a few similar properties for the variance. So again, if we have fixed constants a and b, the variance of ax plus b is equal to, which are, use the notation sigma squared of the random variable a times x plus b, is actually just equal to a squared times the variance of x. So whatever the variance of x was, just take that times a squared. And similarly, the standard deviation there, you can just take the square root of that thing above, and that's what you get. So let's actually give a quick proof here of how we can show that this is true. So again, if we let y equal ax plus b, and we also know the expected value of y is a times the expected value of x plus b. Then the variance of y is equal to the expected value, by definition here, of y minus its expected value squared. That's just by definition. And now we can substitute in what we know from y, an expected value of y. So this is equal to expected value of ax plus b minus a times the expected value of x minus b. So just writing in there what y, an expected value of y, is. And now some things, the b's are going to cancel out there, and we're left with the expected value of ax minus a times the expected value of x, all that squared. And then we can do some. We can pull an a out of that, inside of that parentheses, and this is just the expected value of a times x minus the expected value of x squared. Which we can simplify slightly further, which is just a squared times the expected value of x minus the expected value of x squared. And that should look familiar. That's just a squared times the variance of x. All right, so if we know what the variance of x is, and we have a linear function again of x as in y there, it's very easy to quickly calculate what the variance of that linear function is. You can do it as there. Okay, a few more properties here. No problem. A few more properties. A special case again for constants a and b. The variance of a constant is just 0. The variance of x plus a constant is just the variance of x. So adding on something doesn't change the variance. And again, then what we saw there previously, variance of a times x is just a squared times the variance of x. So these are just some properties that might be helpful to you. Okay, so getting back to our previous example here, our store selling computers example here, same setup here. We can now think about what's the variance of the number of computers sold. So we already know that the expected value of x is 2. So again, to find the variance here, let's first calculate the expected value of x squared. And again, this is just the sum from x equals 0 to 3 of x squared times the probability of x. So again, practicing our expected value of a function of x. And again, x can be 0, 1, 2, or 3, so this is 0 squared times 0.1 plus 1 squared times 0.2 plus 2 squared times 0.3 plus 3 squared times 0.4. And do all those calculations, that should give you a 5. And so once we have expected value of x squared, and the expected value of x, it's very easy to quickly calculate the variance. So the variance of x, which again is sigma squared of x, is just the expected value of x squared minus the expected value of x, quantity, squared, which is again 5 minus 2 squared, which is 1. So the variance, kind of how spread out. Again, this doesn't give you a direct interpretation of how spread out the distribution is, but it just tells you that the spread of this thing is kind of small. All the outcomes you can get 0, 1, 2, or 3 are all pretty close together. And that's the variance. Similarly, what is the variance of the profit of the store? So again, we saw that the profit y, that was 800 times x minus 900, I think. Yeah, so the variance of, we can use our formula now. The variance of y is equal to the variance of 800x minus 900, just by definition again. And now we can use those special cases at the top of your the top of the page in the notes here. This is just 800 squared times the variance of x. So the 900 goes away, the constant doesn't change the variance, and then we can, since we're multiplying x times 800, we can pull that outside the variance and calculate it that way. Again, the variance of x was 1, so this is just 800 squared. Or 640,000. So what does that mean? Well, remember so the units of this thing, the units are dollars squared. So this is square dollars and yeah. So we don't have to subtract the 900. We can sort of ignore that because of this line right here. I should have made that more clear. Yeah. So if you take the variance of something plus a constant, it doesn't change the variance. You kind of just ignore what that is. Great question. Sorry, I should have made that more clear. And then for the second step, we can use, so the variance of 800 times x is just 800 squared times the variance of x. So the units of the variance are in squared dollars, which doesn't make any sense. Like, what is a squared dollar? I don't know. So that's why we'll talk about the standard deviation of y, which is sigma of y, square root of the variance of y again, which is just $800. So that makes a little more sense. So we'll talk more about the sort of what the variance, what the standard deviation, what that means. We'll see that a little more later in the course. But just for now, it's kind of just a intuitive measure of how spread out the distribution is. So if the standard deviation and variance are both really big, then think about that distribution is going to be really spread out. If it's really small, then you can think the distribution is going to kind of be squished together and not much variability there. So we'll talk more about the interpretations later, but this is kind of the calculation here of how we actually find these things. Questions or comments? We all on the same page? Okay, so that's the end of section 3.3. Actually, let's forge on ahead here. Talk to section 3.4, which is called the binomial distribution. So the general idea is, so far in chapter 3 we've talked about sort of very specific random variables. There's been a very specific example and sort of a certain setup. So those come from simple experiments, rolling a dice, drawing cards, flipping coins, all of those things. But some experiments, some random variables show up often enough that they have names and that they have certain properties that we want to talk about and use. And because these you would actually see sort of in a real world situation. So the three things that we'll talk about in this chapter anyway are the the Bernoulli distribution, the binomial distribution, and the Poisson distribution, which that's coming later. So the Bernoulli distribution, I think I said that word to you one time. It was in the, sort of the context of an example. I'll formalize that here. They're very closely related to the binomial distribution. So this is what we'll be discussing here in this section. And this is kind of what we'll do. We'll see this again in chapter 4. There's sort of these very standard random variables that we'll see and that we'll use very often. So we want to talk about their properties. Okay, so here's the Bernoulli distribution. So let's talk about that really quickly. This comes from the idea of a Bernoulli trial. I mean, I know we talked about this before, but have you guys, is that Bernoulli? Is that a word you've heard before? Maybe in a different context. Anyway, it's just an experiment which decides a success or a failure. So you could, again, kind of our classic example is a flipping a coin. You can call a success getting a head and a failure getting a tail or something like that. But it could be anything else really. So the point is that this random variable assigns x either a 1 or a 0. So if we get a success for our experiment, we say it's a 1. If we get a failure, then we have a 0. And again, sort of very simple down here. Its probability mass function can be defined sort of in general here. So the probability that x is equal to 0 or 1 is given there. So if we're saying the probability of getting a success is some lowercase p, and the probability of getting a failure is just 1 minus that probability of success. So let's say p is the probability. P is the probability of success. And we can leave that in general terms now. It can be anything between 0 and 1. We're going to call that a parameter. Okay, so using what we just learned in section 3.3, we can figure out what the mean and variance of a Bernoulli random variable are. So again, the expected value of x which is the sum x can equal 0 up to 1 of x times the probability of x. So again, that's just 1 times p plus 0 times 1 minus p. So the expected value is just p, probability of success. And again, to find the variance, let's first find the expected value of x squared, which is the sum x equals 0 up to 1 of x squared times the probability of each x. So that's 1 squared times p plus 0 squared times 1 minus p. Lo and behold, the expected value of x is actually equal to the expected value of x. And therefore the variance of a Bernoulli random variable is just the expected value of x squared minus the expected value of x, the whole thing squared, which is just p minus p squared, or p times 1 minus p. So the expected value of a Bernoulli random variable is its success probability, and the variance is p times 1 minus p. Pretty okay with those calculations? Kind of quickly went through those. Okay, so that's sort of very simply the Bernoulli distribution, or a Bernoulli random variable, which kind of leads us into this idea of the binomial distribution or a binomial experiment or something like that. So this is if we have a sequence of n Bernoulli trials that have two properties. First of all, the outcome of each successive Bernoulli trial is independent of the other ones. And I have the same probability of success in each one of those experiments. So if I have n Bernoulli trials such that they're all independent and they have the same success probability, that's going to be, and then I'm looking at the overall number of successes that I get. That's called a binomial experiment. So I have n of these Bernoulli trials and looking at total number of successes out of those n trials. Yes, so here we go. So then x is the number of successes in those trials. And in this case, then we're going to say x is a binomial random variable. So this is kind of our first main class of random variables here. And its distribution depends on two things: the number of trials that you have, n, and the probability of success, which is p. And then the notation we're going to use here is this thing, and this, how you can read this is x is distributed as a binomial random variable with n trials and success probability p. So when you see x with a little squiggly line, that just means x is distributed as a binomial random variable with n trials and p, and probability of success p. So for example, if you were selecting 6 soft drinks and kind of looking at, I don't know, do they still do that? Do they still have prizes under the caps of soft drinks? Yeah, maybe it's more of like a 90s thing, I don't know. But if you can remember that, then if you're looking at 6 of these things at random and seeing, checking the cap to see if you want a prize, then that would be a binomial random variable. So assuming there's only one type of prize and that you have the same probability of winning for each one of those bottles. That's an example. Sort of the classic example is a coin toss. So if you flip a coin 10 times, and you count the number of times the coin lands on heads, so you'll be calling. So here a success would equal a head. So you're flipping the coin. Each time you flip the coin is independent of the other times, right? The coin doesn't know what it was flipped before. So you have independent coin flips there, and each one has the same probability of landing on heads. So if x is the number of times you get heads, then that you could think about that as a binomial random variable with 10 trials and success probability 1/2. So sort of just very, very simple examples here for what this thing is. So let's consider if we want to derive the PMF of binomial random variable, we can start small. So if we have a case where x is binomial with 3 trials and success probability p, so I'm going to do 3 trials, and I'm going to see for each one of those trials, I'm going to see the success and the failure of that trial, and then count up the number of successes that I get. So here, again, x equals the number of successes. So imagine if we're back in chapter 2 or even chapter 3 here. I guess chapter 3. We could list out all the possible outcomes of those 3 experiments, of success or failure for each one of them, and then we could figure out the probability of each of those outcomes. And so so the sort of the key idea is that we're using independence. So the probability of getting 3 successes is simply p times p times p, p cubed. The probability of getting the SSF outcome, the second line there, is I need 2. I need my first one to be a success, so with probability p. Second one needs to also be a success with probability p, and then the last one I will have a failure. So that's 1 minus p. So I'm just kind of multiplying these probabilities together. Maybe I'll write that down. So the probability of SSS, for example, is the probability of S times the probability of S times the probability of S. So I'm using independence here to find those probabilities. And there I can go through each one of my outcomes. You can see that, for example, SSF makes x equal to 2, just like SFS. So there's different outcomes that give you the same value of the random variable there. Different outcomes give you a 2. And so I could calculate all those things. So for each one of those outcomes, there's the probability of each thing happening there. And so maybe a question for you here. If I'm looking at, if I'm thinking about the random variable x, do I care about the ordering here? So I'm counting up the number of successes. Does it matter what order those successes happened in? No, it doesn't, right? So just a note that x does not consider the order. That's why, again, you have different outcomes give you the same value of the random variable. Okay, so again, kind of formalizing from that table up there, the probability that x equals 0, that's probability that you got all failures. So we already saw what that probability is. The probability that x equals 1, we had 3 different outcomes that gave us x equal to 1. So you can just add up those 3 probabilities. Probability that x equals 2, again, there were 3 outcomes that gave us 2 successes. So you can add up those 3 probabilities. And the probability that x equals 3 had to get all successes. So again, there was just one outcome there, and that was p cubed. So sort of in general, the way to think about this in general is that the probability that x is equal to some little value x is equal to the number of sequences of length n that have x of those things being successes, and then times the probability of any one of those sequences. And there's kind of a generalization there. The probability that you get x successes and n minus x failures. Again, we can just multiply all those together, and we have x successes and n minus x failures. So that's probably one of those sequences, and then we can go back to our counting strategies to figure out how many sequences of length n have n successes. And that leads us to a general form for the probability mass function of a binomial random variable. So again, I have now shown it to you, but it's also in your notes. So what's our former notation for this thing? What's the number of successes of out of length, number of sequences of length n with x successes? Again, I don't care about the ordering. So which am I? What would that be? Yeah, it'd be our combinations, right? We don't care about the order, so we're looking at a combination instead of a permutation, and that's just going to be our n choose x. So I have n items, n total experiments, and I want x of those to be a certain way. So I want x of those to be successes, so that'll just be n choose x. So that's where the combination comes in there. So for any x from 0, again, I could have out of n trials, I could have 0 successes. I could have 1, 2, 3, all the way up to n, and otherwise the probability mass function is going to be 0. Trivial case there. And just to throw some additional notation at you here, this is another notation that we're going to use, which again just means that's our PMF for a binomial random variable. So we'll use a b x colon np as another way to denote what that PMF is. Okay, so I'll do an example here in just a second real quick to finish up. But I'll just quickly say, so whereas before we would use the PMF to calculate the CDF, and so we did that in one of the examples at the end of section 3.2, I guess. There's no way to easily calculate what the CDF is or there's no sort of closed form way to say what the CDF is. So again, the CDF is equal to the probability that x is less than that value x. So this is the sum from, so let's use a different index y, the sum from y up to x of the probability of y. So that would be our CDF, and this is y equals 0 up to x of n choose y times the p to the y times 1 minus p to the n minus y. And there's the unfortunate thing is there's no sort of, I mean that's as simple as you can get. You can't simplify that any further in general. So if we want to, when n gets really big and you have to calculate some large range of values, we can use, there's sort of two methods. We can use either a calculator or a computer, or you can use a table. And so I guess about out of time, we'll actually look at that on Monday. But let me quickly note that if you do want to use a calculator, if you have like a TI 83, 84, something like that, or 84, you can do a Google search for either binom PMF or binom CDF. Those things will be little helpful tricks. If you have a TI 83, 84, probably the other ones have ways of calculating that too. So we'll do an example. Sorry, I ran out of time again. No example to finish up here. Look at this on Monday. That's it. Thank you guys so much for being here. Stay warm out there, and have a great weekend.